My name is Corbin Matthews. I'm a master's degree candidate at the Georgia Institute of Technology, and today I'll be presenting on false data injection attacks against railway traction power systems. I'd like to acknowledge the authors who initially presented this work in 2016 at the 46th Annual International Conference on Dependable Systems and Networks. We'll begin our discussion by looking at how urban railways are powered. Electric trains can be powered by either AC or DC, alternating current, direct current. Because we're looking at urban railways, we're going to be focusing primarily on DC current today. And these trains can be powered by overhead electrical lines or third rails. And local substations are required to convert the AC power from the grid to direct current to power the trains. And as we'll talk about later, they're also responsible for converting it back from DC to AC. So what is a traction power system, a TPS? Electrical equipment relies on a consistent power supply. In this case, we're going to be focusing on voltage because it is direct current. And when the train is accelerating, the TPS manages how much power is drawn from the electrical source. As that train is tractioning, accelerating, it is pulling current from the line, and the nodal voltage, the local voltage experienced at that train, decreases. And so the overcurrent control prevents the voltage from falling below a safety threshold. Alternatively, during regenerative braking, the TPS manages how much power is supplied back to the lines or third rails. This squeeze control prevents voltage from exceeding the safety threshold because as the train is regeneratively braking, the nodal voltage, the local voltage around that train is increasing. We're now going to break down how overcurrent control works. So again, as the train is tractioning, it is drawing power from the network, causing a voltage drop at node I. The actual power drawn by the train, PI, is what we're going to be calculating here, and that is to contrast with P sub I with the D superscript, which is the power demand of the train. That is what the conductor is asking for as they are tractioning or accelerating. Also notable here are the nodal voltage and then the safety threshold. That is an established uh, minimum voltage acceptable in that line, and then a voltage trigger. When voltage is above that voltage trigger that we just talked about, the power demand of the train is equal to the power drawn. The next one is an easy one. When the voltage is the nodal voltage is below the minimum safety threshold, the train does not draw any power. So P sub I is 0. And now we're going to look at how much power is drawn by the train when the nodal voltage V sub I is between our safety threshold and our voltage trigger. So in this range, the amount of power drawn is going to be scaled down based on how close it is to each of these thresholds. And this will make a little bit more sense when I plug in some numbers for an example on the next slide. In this case, the nodal voltage is 450 volts, the minimum threshold is 400 volts, and the voltage trigger is 500 volts, which leaves us with 50 volts in the numerator and 100 volts in the denominator. So we are scaling our power demand by 50%. So in this case, the conductor is getting 50% of the power that they are requesting. Alternatively, you can imagine that if instead of 450 volts at our node, if we have 401 volts, our denominator is going to remain unchanged and our numerator is now going to be 1 volt, which is going to leave us with 1%. So the conductor would be getting 1% of the voltage they request when our nodal voltage is just 1 volt above that safety threshold in this example. Squeeze control controls how much power the train injects back into the network when the train is regenerating. We'll have some similar figures here as far as actual power drawn, or rather injected P sub I, and then our regenerative capacity of the train, P sub I with the C superscript. Instead of a minimum threshold here, we have V sub I max, so our maximum allowable voltage, and then we also have a voltage maximum trigger, at which point, when we hit that trigger, we are going to begin scaling back the amount of power injected into the grid. Similar as last time, the first two are going to be pretty easy. So if we're already above whatever our safety threshold is, there's going to be no regenerative braking, no energy sent back into the line. If we are well below our threshold where we begin scaling it back, we're going to deliver the full amount of regenerative capacity of the train. And then in this middle case, again, we will scale the regenerative capacity of the train, P sub I with the C superscript, by the scalar that we calculate in the parentheses here. So we've talked about what TPS is and how it works, and you understand overcurrent and undercurrent, or rather overcurrent and squeeze conditions. So why does TPS matter? In 2014, Moscow Metro derailed, causing, due to sudden braking due to a TPS malfunction. This resulted in 24 fatalities and 160 injuries. In 2015, Singapore experienced TPS faults, resulting in a system-wide disruption to almost 500,000 commuters. The effect of TPS is profound as far as safety. It can affect the efficiency of the train, as well as the economic impact of reducing the perceived safety or confidence in public transportation. Finally, because electrical equipment relies on a consistent voltage and a consistent power supply, surges or dips or sag in that electrical supply can damage electrical equipment, which can also result in economic impact. So what is the problem? The sensors used to coordinate and control railway operations, including TPS, are vulnerable to cyber attack. Methods to compromise these sensors include remote interference, compromised manufacturing, as well as compromises in the firmware. As alluded to in the previous slide, this threat model includes electromagnetic, remote interference, and analog systems. It can act at a distance of 1 to 2 meters. Additionally, by Kirchhoff's principle, it's worth considering that and assuming that the attacker has accurate knowledge of the system, including relevant models, parameters, and methods of detecting an attack. And this is substantiated by real-world attackers who have demonstrated both long-term data exfiltration as well as extensive social engineering of employees, vendors, contractors. With respect to the second bullet point in this list, the hardware Trojans and chips, it's worth considering this specifically in regard to supply chain risk and how equipment is manufactured or subcontracted out to be manufactured. For our last point on the list, malware infections and sensor firmware, these can either be built into the system or transmitted into the system by some means. Existing mitigation tactics for this have relied on air gapping the information and communication technologies for railways. However, there are proven compromises of air gap systems, both with Stuxnet and Dragonfly. In the case of Stuxnet, this was an example of a false data injection attack. A false data injection is an attack on the integrity of information. With respect to TPS, we'll be looking at tampering with system measurements. And the two types of attacks we'll be concerned with are safety attacks, which cause unsafe voltage conditions in electrical systems, and then efficiency attacks. And in this investigation, it was identified that without some of the mitigation techniques we'll discuss later, a 28.3% increase in energy consumption is possible. In this example of a safety attack, false data injection was employed to artificially produce low voltage readings, causing the nodal voltage, the real nodal voltage, to increase beyond the safety threshold. And you can see here in the V sub I column, the actual voltage is 901, whereas the V sub I prime reading that is falsely injected is 862.9. And this is with respect to a 900 volt maximum safe threshold. For efficiency attacks, we're first going to look at providing a falsely elevated voltage reading. Because the power that is able to be regenerated back sent back to the lines is based on the voltage and not the current. Increasing this voltage from 847.7 to 888.6 has decreased P sub I, the amount of power that is sent back. And in this table, we are assuming that the only compromised node is node number 2. If you look at node 2 in the P sub I rows, you'll notice that the amount of power returned to the grid is dramatically lower between the efficiency attack and the natural state. You'll also notice that the amounts of power in adjacent nodes is affected. So for instance, node 3 in the efficiency attack, because node 2 is no longer contributing so much, we actually see an increase in how much regeneration is provided from 1.16 about to 1.8. And additionally, in nodes 1 and 4, there is less capacity to draw down current from the line in tractioning, and you see 1 and 4 have a reduced. Lastly, note the difference between the regenerative capacity in nodes 2 and 3 in the TPS state, and how node 3 is now fully utilized during our efficiency attack because node 2 has freed up so much of that extra regenerative capacity. Now that you've seen how the attacks can affect the surrounding nodes, let's look at how to craft this false data injection attack. The first step is to calculate power injection or draw using compromised V sub I prime, compromised voltage measurement. Using Ohm's law, you can use this to calculate the power and either set or specify the current. Typically, you would want to identify how much power you want to feed into the system, and then proceed to identify your voltage and currents. It's worth noting that some trains can measure power consumption, not just voltage, so a false current reading, I sub I prime, also needs to be calculated. The second step is to verify P sub I is within the range of what the train can regenerate or draw from the system. In the previous example, you saw that the trains could regenerate respectively 5.5 or 1.8 units of power. If you exceed that, then the actual power drawn is not going to reflect your intended attack. For the third step, is to verify that the compromised voltage and current measurements you've provided are within the maximum allowable error. So in these two equations, you see VI prime, or rather V prime and I prime. So the false voltage and current measurements have to fall within a certain range of the true voltage and current measurements. And you'll see that this is represented by the delta V and the delta I respectively. Now that you have your system of equations, the next step is to solve this constrained optimization across all nodes to achieve the power and state of the system as intended. The authors propose the global attack detection system, which is comprised of state estimation, bad data detection, and secondary attack detection. Bad data detection and state estimation are widely used in AC grid to reduce the effect of noisy sensors and to detect faulty equipment. Secondary attack detection will detect false data injection on voltage and current measurements. State estimation and position integrity validation require the data is validated from multiple sources. Nodal voltage can be calculated based on measurements from local substations by looking at the false voltage number provided and comparing it to V sub NL, which is the voltage with no load on the system, as well as looking at the resistance through that section of wire or rail um, times the measurement of current drawn. Train position can be validated by a train-borne wheel sensor, GPS, and trackside balise. These systems work in tandem to provide for GPS near instantaneous position information, and then the train board wheel sensors and the trackside balise work in conjunction to provide reckoning to identify where the train is. As noted in a previous slide, bad data detection is employed in AC systems. The novelty of this paper is the domain-specific design and the application of two DC circuits. So bad data detection means that large attacks are detected and or attackers must tightly constrain their attack to remain undetected. The method of doing this is to calculate a system state, which we're going to represent as V, which is a vector of our true voltages. And we're going to represent that as Z, which we calculate through a measurement matrix H um, based on the true position S of all nodes in the system. We'll multiply that again by V and add in N, which corresponds to an allowance for random noise in the system. The next step is to create a maximum likelihood estimation of voltage, and then to compare that maximum likelihood estimation and raise an alarm if the measurements of voltage and current deviate from the expected values. And this will be compared to a tau value. And this tau value should be configured so that false positive results are tolerable and minimal. One limitation of BDD is that it can be bypassed if an attacker is willing to compromise on the extent of the attack and constrain it. Given this equation here, Y of S is an N by N nodal conductance matrix, which is based on the inverse resistance or conductance between each set of nodes in the system. To constrain this attack, means limiting the voltage and therefore the amount of power. Given the complexity of compromising position data as prime, this system is frequently constrained by an additional degree because sensor data cannot be reliably manipulated when it is able to be verified by GPS, train wheel sensors, as well as balises. Secondary attack detection can also be represented by a system of equations to constrain the attack. If train position is fixed, then the system of equations is expected to have a finite number of solutions because there are two variables to solve for and three equations. The first equation in the secondary attack detection is Ohm's law, that is the voltage times current equals power. We've looked at that extensively throughout this discussion. Second, the TPS can check data from local substations, and that false voltage measurement can be compared to the no load voltage measurement and reduced by the amount of expected resistance in the current. And similar to BDD, the tolerance of the system does come in here. To complete this detection, you'll use the three equations and first use the nodal measurements of current and voltage to compute P sub I for each of the nodes. Second is to solve the constrained equation for J using the following equation for C based on the resistance and local voltage. The current time state in step 3, the current time state of the system is compared to the previous time state, and this is compared to our J star term to determine whether there is whether to report no attack or whether to report an attack. The results of the first of these two systems are shown below. The effect on the efficiency of these attacks is greatly diminished when BDD is present. If you look at the two graphs, the top graph where BDD is absent, there is a much larger gap between the power injected into the system, the green lines or the green and red spikes, versus when the BDD is employed and the green and red positive voltage when the current, or rather power, is being injected back into the lines are much closer together. For secondary attack detection, at each time point, if the red dot is below the blue dot, then an attack was detected. And you'll notice here, almost all of the blue dots are above the red dots, recognizing that per our equation, J is less than the result of subtracting these two voltages. To summarize the findings, TPS systems are vulnerable, and the proposed solution by the authors is successful in detecting many attacks. BDD, it detects large attacks successfully, and as demonstrated in this investigation, the efficiency of these attacks cannot exceed 6% without being detected. As a second line of defense, secondary attack detection detects 96% of attacks that bypass BDD.